Hey everyone, in this video we're going to take a look at the ultimate web researcher using Exa web search API. This does a lot of cool stuff, very perplexity-like. It performs multiple web searches, then actually chunks those searches, performs similarity search across multiple queries, and performs rerank. Let's first see how it works, and then we're going to actually review the diagram for it. And I'm going to explain exactly what is happening because there's quite a lot that takes place. But let's just run this question. What is the size of the latest budget proposed for the state of California? And then it asks us how many days backwards we want to search for. We can say 3, meaning we want to search the web for the stuff that is within the last 3 days. Then we have our original question plus GPT writes for us 3 alternatives. An alternative question, a statement form of the question, and then some keywords and phrases. And we take all of those, a total of 4, including our original question. Then we perform Exa search, 10 searches for each. And then when we receive the search results, we save them into their appropriate results JSON file. And then we also chunk them, 800 tokens each, into chunks.json. Then we actually sort those chunks, performing similarity search based on all of the queries that we have generated. We're essentially performing re-ranking. And then we re-rank again to see how many of the top 5 chunks appeared for the search for each of the search results. And then we count them, and then we re-rank them again here. And after that, we send this top 5 chunks to GPT to get an answer. And here's our answer. The latest budget proposed for state of California is $297.9 billion. And if I actually look at the budget agreement, it does say that it is $279.9 billion. Now, after this step, since we have saved the chunks.json, we can switch to the local search. This local search will use the chunk.json, which includes the chunks of all the search results that we have retrieved. Total of 4, it should be approximately 40 of them. Then we can ask, for example, what is the breakdown of the budget? And then now it again performs alternative query searches for re-ranking, and we save those into local search. And then we get a breakdown based on the top 5 chunks again. So this is pretty cool. It's an experimental approach implementing some of the ideas I had. So it's very nice. This uses Exa, but you can imagine using any other search provider such as Brave or Serper. The logic remains the same. The cool part is that we perform a lot of searches and simulated searches to rank and re-rank the chunks. I'm going to explain everything here on this diagram, and then we'll review the code. The code files for this project will be available for download for my supporters at Patreon. The link will be in the description and the pinned comment. Do check it out if you like. I would like to take a moment to talk about the benefits of becoming a patron. As some of you may know, in the last year and a half, I've spent 3,000 hours, over 300 projects as a patron. You will have access to all the code files so you can get inspiration and iterate quickly. Another benefit is that you'll have access to all my courses. And my most recent and most proud one, the 1000x MasterClass, teaching what I've learned on how to code fast and efficiently. Also the Streamlit course and the Fast API course. In my Patreon, I also have tiers in which you can connect with me one-on-one. Check those out as well. So let's start with the review of the diagram for this code. This is called the Ultimate Web Researcher with Exa and GPT-4 Omni. I use GPT-4 because of its JSON mode, just makes things more convenient, but you can use Claude as well by changing a few lines of code. So essentially, we first take in a user question. Then we send that question to GPT-4 for it to produce an alternative question to our question, a statement form of the question, and key phrases for this question, such as keywords and key phrases that represent the question accurately. As you can imagine, you can generate as many as you like. Here in this case, I just opted to 3 alternatives. Then we get our original user question too. So now we have 4 queries that we can perform when we call Exa Search API. And when we call that, each one returns up to 10 search results for each. For example, these are the results for the user question. These are the results for the alternative question. These are the results for the statement form, and these are the results for key phrases and whatnot. Once we receive these search results, then we actually chunk them all into many chunks, however many there might be. So we take each one of these results and chunk them into 800 tokens with 400 overlap. That is what OpenAI's Assistant v2 API uses. So that's what I went with. But you can change this chunking strategy in the script easily. So once we have our chunks, then we actually perform cosine similarity for each one of the queries we had: the original user question, the alternative question, statement, form of the question, and the key phrases for the question. So we perform similarity search across all these chunks and we sort them into top 5 chunks. So we end up having 20 top chunks, but 5 for each one of the questions. So once we have that, we actually want to count how many times each chunk appears in each one of the top 5 chunk groups. So this is the re-ranking portion of it. How this works is script takes the first chunk and counts how many times it appears in these. Okay, like does this chunk appear in this search result? Did it appear in this top 5 simulated search results? Did it appear in this? And then it does it for each one of the top chunks. And then it counts them and then puts it into a dictionary. So now we know how many times each chunk has appeared. And then we sort them. Then we'll have something like a final top 5 chunk is looking something like this. This chunk appeared like, let's say 5 times. This second chunk appeared 4 times. This chunk appeared twice, and the rest was 1. So after the re-rank, this is the final top 5 chunks, and we use that as context to send to GPT-4o, and then we get our final answer based on the original user query. So this is very cool. It's very modular. I actually based this on the project I did based on the auto rag chat video that I published. I used a lot of the functions from there. Take a look at that if you want to dive deeper into it. So now let's actually review the code and see how all of this are taking place. Before I continue, I can show you the top 5 chunks, for example. Here, after we perform the final re-ranking, this particular chunk, for example, appeared in all of the search results, and the next one also did. The last one only appeared 3 times. So this is how we perform re-ranking. So this should give you some ideas on maybe how Perplexity works, or you can actually perform your own interesting search methodology, because there's no limit to how many queries you can generate. By the way, check out my website. You can find all my videos there easily with a search, fohive.live. But remember that we are generating these 3 alternative queries, but we could have generated 10, for example. Then we could have performed 10 extra search options and we could have had additional re-ranking abilities, or we could have re-ranked it into top 10, for example, if you wanted to increase the context that you're sending to the model. So this works really well. Let's begin by reviewing the Ultimate Web Researcher, and the local search is actually mostly the same as Ultimate Web Researcher, but it just uses automatically the chunks.json file, which are generated by the search results we have retrieved from the Ultimate Web Researcher. I would like to take a moment to talk about the benefits of becoming a patron. As some of you may know, in the last year and a half, I've spent 3,000 hours, over 300 projects as a patron. You will have access to all the code files so you can get inspiration and iterate quickly. Another benefit is that you'll have access to all my courses, and my most recent and most proud one, the 1000x MasterClass, teaching what I've learned on how to code fast and efficiently. Also the Streamlit course and the Fast API course. In my Patreon, I also have tiers in which you can connect with me one-on-one. Check those out as well. The requirements for this project is OpenAI, Exa API, and term color. And we are doing all our imports at the top, and we define a token encoding model. This is for tick token. We do need tick token as a requirement as well. We can use tick token to actually count how many tokens we are consuming. And then we specify an embedding model, which is we're gonna use OpenAI Sticks embedding 3 large. And our first function is get Exa instance, which returns an Exa client, and get OpenAI function, which returns an async OpenAI client. And then we have a function to modularly craft our messages list. Define messages list takes in a system message and a user message, but you can leave the user message off. I suppose you can pass the context directly in the system message. So this function, based on whether user message or system message provided, returns a list of messages. we're not keeping track of any message history in this case. Then we have a async function called GPT-4 with streaming and JSON mode turned on, which is going to take in messages. And this function, we're going to use both with JSON mode on and off. That's why we're passing this keyword argument. And we get the client by calling the getOpenAI client function, which we have defined. Then we make a call with, if JSON mode is true, we make a call with the messages list using JSON mode, or just otherwise just regular, both of them rich, using streaming responses. And now we get the assistant response. We append the streaming chunks into it and return it. We have a function to get a date cutoff. So this just uses date time. Remember when we were performing web research, it's asking us how many days we want to go back. So this just performs that for us automatically. By default, it's 30. And now we have Exa search function, which is going to take in the Exa client, and then which we are going to define using the get Exa instance. And then it's going to take in a user input, a date cutoff, and a number of results, default 10. Then we're going to do search and return contents using async.io to thread, because we're going to perform these searches in parallel. So when we call this function one time, it's going to create a new thread, so we can perform many searches if we want. We pass in the user input. We specify the type magic, because Exa API has keyword search and neural search. When you can put in those here as well, but if you put in magic, it actually decides for itself. We do usually use auto prompt set to true, because Exa actually reformulates your questions. If you read more about Exa AI, it does this interesting way of searching the web. But we use the auto prompt true, so that Exa actually converts our queries to the way that Exa thinks works best. Number of results is going to be 10. We set text to true, so that we actually get the contents from Exa as well. And the start publish date, we set it as the date cutoff. Okay. And then if there's any error, we return that. We have a sanitize file name function, because we're going to take the queries and sanitize them by the first 30 characters. That's how we save them into search results, so you can actually know which file corresponds to which query. Okay. And so these are the results that Exa returns, along with the URLs, ID, title, author, and the text content of the page. Okay. Continuing, we have a save results to JSON function, which is going to take in search results list, which is returned by Exa. As you can see, this is a list of objects, and then since there's some keys, we're going to actually write it as a JSON object using the ID, title, score. That's how we are able to write it here like that. So this function simply is just going to write it using JSON. And now we have this count token function, which I think having some issues currently, but it just uses tick token, using the token encoding model to actually count the tokens and return for whatever text. And then we have a text splitter function, which is going to take in some text and use the tick tokens encoding model. Yeah, that's right. I forgot that we are using tick token to also split the text. And we use GPT-4 encoding to split the text into a chunk size of 800 and overlap of 400. You can change these, and this function will take care of it for you. And then we just return decoded chunks. And once we have all of them, then we save them to chunks.json file. And you can see the 400 overlap here. If I zoom out and start selecting parts of this, should see that it's actually, this part is apparent in the second half of the first chunk as well. That's due to the 400 overlap. And then the next function is embed text chunks, which is going to use again OpenAI client and just simply call the embeddings endpoint. And once we get a response for a chunk, then we're going to actually return a dictionary called with text and embeddings. We're going to actually save this we're going to have this in memory, but we're going to have the chunk and its embeddings. And we perform this by using async.io. We call the embed chunk async function, which we define under embed text chunks. We call it for all the chunks. And then we simply return them as embedded chunks in this format. Then we save this. We have a helper function to save chunks to file, to just chunks.json. And now we have another function to embed the query. Again, this just calls to the embeddings endpoint and returns the embedding for our questions. And now we have the cosine similarity search, which takes in a query embedding, the embedding form of the query and embedded chunks, and actually performs similarity search using cosine similarity from scikit-learn, and actually returns the top 5 most relevant results based on cosine similarity search, and save top chunks to text file, saves the top chunks text. You can see this is the top 5 chunks. I'm actually saving it twice, but no matter. Then in our main loop, we instantiate our Exa client and we take in a user question, whatever question user may want to ask, and then we check how many entered number of days to go back from the current date. So if your question is more general, maybe you want to keep a wider window. But if you're looking for something that is immediately relevant, such as like the budget proposed for California, you can set this to 1 day, 2 day, or 3 days. System message for alternative queries. So as we're saying, this is our system message. Your task is to rewrite the user query in 4 different forms, actually 3 different forms, from which forms which represent well the original query. Here are the 3 alternatives we're looking for: an alternative of the question asked in a unique and creative way, a statement phrase of the question, a unique statement that represents the original query, and keywords compilation. Since we're going to use JSON mod, we are asking it to return in a JSON format such as this. And then we pass in the user queries. As you can see, we're directly passing in the system message. So this one's not going to require a user message, for example. And then we define the messages list by passing the system message for the alternative queries and the user question. Then we call GPT-4o with streaming JSON using the messages. We have defined the messages list, and then we generate the alternative queries. Then we JSON load the alternative queries, and then we add the user question to the list of alternative queries values. So we add our original user question since GPT returned 3 alternatives. Then we simply print them for viewing, and then we get the date cutoff using the getDate cutoff function. And then we perform our search tasks by defining the tasks list, which is going to be Exa search called for query for all of the queries. Here you can actually, if you want to test, you can limit the amount of queries to the first 2 or the first one using index splicing. But if you just leave it as it is, it will perform on all queries. And then we wait for those tasks to be completed, and then we'll have our results as all results. Then we create a search results folder if it doesn't exist, and then we save each search result for each query into its own file. So here we loop over all the queries and all results and get the query and the result. We sanitize the query so that we don't run into any issues as far as how you can save the files. That's what the sanitized file name does. We talked about that. And then we simply define a file name and pass it to save results to JSON, which then is going to save them like this. All the results that was returned for this particular query, how large is the most recent. We are only sanitizing the file name to the first 30 characters. And then we want to now chunk the text of each result, save it to a single chunks.json file. So we create all chunks list and we go through all of the results. Each of the results as they are becoming available. As you can see, this is a loop within a loop. And we pass it to the text splitter, and then we extend the all chunks list, which we had defined somewhere here. Oh, right here, all chunks list. So we go through all of the results for each query and add them to the all chunks list, and we call the save chunks to file, which is going to save all of our chunks into this single file, just like this. And then we're going to embed the chunks by calling embed text chunks. So that's why this is very modular. It's going to embed all of our chunks, and we're going to have a vector DB in this embedded chunks. Now we're going to perform cosine similarity using each query that we have. We first initialize an empty dictionary, and we loop over each of the queries that we have, total of 4 in this case, and then we embed the query and perform cosine similarity across the entire using the query embedding and the embedded chunks. And then we all sorted chunks query is going to include the top 5 results for that. So all sorted chunks is going to include top 5 search results based on each of the queries. And now we save them as the sorted chunks. So for example, if the search results were how large is the most recent, right? We first split this into chunks and then perform cosine similarity. And then this is the top 5 results, top 5 chunks for this particular query. And the same is true for each one of the queries. So that's what we do here. And then check this loop here is going to check how many times each top chunk appeared in the top 5 of each sorted chunks. So we have 4 top 5 chunks, right? We're going to take each one of the chunks and see how many times this has appeared in all 4. This we are hoping is going to return the most relevant chunks, because since we have 4 distinct queries, we are expecting the most relevant chunks to be returned the most. So we pretty much loop over it, and top 5 chunks, we first create a top chunks count dictionary, and then we get each chunk and then loop over each one of the other lists JSONs that we have. And then if we find it, then we increase its count by 1. And otherwise it's just going to have appeared only one time. And then grab the top 5 based on the count. So we just perform this inline operation to actually get the top 5 chunks, which is the final top 5 chunks after our re-ranking operation here. And now we save them to top 5 chunks.json right here. So these, you can see this particular one has appeared 4 times in the overall search results. So we're hoping that contains relevant information. We are also saving them to top chunks count.json. I guess this is redundant, but nevertheless, you can delete that if you like. Then we make a call to GPT with these chunks. And to do that, we create a new system message. You are an expert at answering questions. You are provided with the following context. We pass in the top 5 chunks. Your task is to answer the following question, which is the user question. If the exact question user is asking cannot be answered from the context, then explain that you cannot answer the question. We call again the define messages list, which helps us create message lists for API calls. We pass in our parameters, and then essentially we try to print the number of tokens in our message here, but this sometimes have hiccups. And then we pretty much call and get our response. This automatically prints. A JSON mode is false because we're not looking for a JSON object. We pass the messages. Since this is streaming, it will automatically print to the terminal, but we are not really doing anything with its output. So for this, you are relying on how well the Exa returns search results. So if Exa doesn't return good search results, then this, of course, is not going to work well. But as you can imagine, if we go back to our diagram, we are using Exa search, but there's no reason why you couldn't use multiple different searches using different APIs such as Brave, or just keep that in mind. You can actually perform another layer of complexity. Maybe this can be Brave, maybe this can be Perplexity or Serper API. Just keep that in mind. I tried to keep everything modular so you can improve on it. Now, the local search does pretty much everything the same, except it just loads the chunks from chunk.json. Okay, so this doesn't have the part where it performs web search. But other than that, in our main function, we still call GPT for alternative queries, so we can perform cosine similarity based on all those queries, and everything else remains the same for this. Okay? So if you run this ultimate web researcher once, then you're going to perform 4 different searches, and all the chunks will be stored here, and that's all you need to perform cosine similarity, and local search will pick up from there. You can ask additional questions using local search. Like I said, this is a bit experimental, and I wanted to really explore different ranking and re-ranking ideas. As you can see, this is very modular, and you can actually improve this at every step of the way if you wanted to. But just do know that this relies on the results that are returned from Exa. If you're not getting the answers you're looking for, do make sure to investigate these search results and see if actually the Excel was able to return the relevant information for you to answer the question. I would like to take a moment to talk about the benefits of becoming a patron. As some of you may know, in the last year and a half, I've spent 3,000 hours, over 300 projects as a patron. You will have access to all the code files so you can get inspiration and iterate quickly. Another benefit is that you'll have access to all my courses, and my most recent and most proud one, the 1000x MasterClass, teaching what I've learned on how to code fast and efficiently. Also the Streamlit course and the Fast API course. In my Patreon, I also have tiers in which you can connect with me one-on-one. Check those out as well.